So, switching losses, we already had talked about gate driver switching losses and then dead time switching losses, and gate driver switching losses, it does not depend on your load current, while your this dead time switching loss depends on load current and the basically non overlap time, okay, and switching frequency as well. So, it depends basically how much percentage of 1 clock period you are basically spending into dead time, that will define your switching. So, that is we always try to minimize that dead time in order to get better efficiency. So, this is also associated with your power FETs. So, this is your P FET and this is your N FET, and this is mostly associated with high side FET or PMOS. NMOS will also have some hard switching losses, but that will be much less compared to PMOS. So, the dominant will be the PMOS. So, if this is PWM, I will say it bar, okay, because gate this will be high when. So, VSW if you want to keep high, then PWM bar should be low, which means PWM is high. So, VSW is high, sorry, okay, because it is a NMOS and PMOS complementary. So, both should be PWM bar, and you can assume they are non overlap. Whenever I write both, they are non overlap actually gate, but just for simplicity I write the same signal. So, when PWM is high, your VSW is going to be high, correct? Or let me write it V gate, because I want to V gate N, okay. So, let us call it V gate. So, this will go low here. So, I mean that is how we usually write, but if we zoom in this portion, actually this portion I want to zoom, okay. So, how will it look like? So, let me just expand this here. Okay. If you have a closer look, usually this is a very small fraction of your fall time of the gate of your period. So, if you draw the whole clock period, it will look like okay, transition is very fast, but if you zoom in, what would happen? You will have some rise time associated with it, okay. So, this is your V gate and not rise time, but T fall. Rise time will be your VSW, okay. So, how will your VSW change with this? It will start rising at when? When will this transistor turn on? So, this is your VDD, this is your 0. So, first thing it has to cross VTP, threshold voltage, okay. Then will this VSW start rising right away? Yeah. So, what happens when you turning on where the current is going? So, current is flowing into this, and what is this current? This current is, just ignore ripple, this is your I load, and VSW is that time minus VF, forward voltage of the. So, which means unless you reverse bias this diode, it will not rise, correct. As long as diode is conducting, this voltage will be maintained at minus. So, this body diode has to be reverse biased in order to have VSW rising. Okay. So, which means not right at, because when you cross the BTP, the resistance looking at the drain of this will be very high, RDS on. So, if RDS on is very high, it will not be able to supply enough current to turn the diode forward bias, correct. So, which means it will happen closer to your, when you are actually 0, which means your resistance becomes so small that diode becomes reverse biased and turns off, then your it will start rising VSW. Okay. So, what will happen to the VDS of this power MOSFET? So, what is the VDS here? VDS of P, VDD plus VF, correct. If you look at the textbook, they will not take into account this VF factor, but not it will be VF. Okay. When this is on, then VDS will be VF plus IR drop of that, but since before you turn on the PFET, your body diode is already conducting, that is why it becomes VDD plus VF. Okay. But usually they consider that this is a 0 volt, okay, which is in reality it is not true if you want to have but this is a not a small amount like 0.7 or 0.6 volt. So, you have to consider that. Okay. Then what would happen to the current? IDD P. So, it will start rising, correct, and where will it go? Ultimately, at what current this IDDP will settle? I load. Okay. So, it will start rising when it crosses so as soon as your gate voltage so the difference between your gate and source becomes threshold voltage, then it will start rising. So, let us say this is the point where you cross the threshold voltage, and this is the point where your it becomes high load. So, ultimately what will be the final voltage? VDSP. What will be this voltage? I on P, sorry, IDDP, it is I load actually, IDDP into R on P. Okay. So, if you take the product of this, the power across the MOSFET. So, if I want to PDS drain to source of P, how will it look like? The current is, so voltage is dropping here, current is rising here. So, the current is 0 here, it will remain 0. So, at this point it will start rising and it will peak somewhere here, Okay. No, sorry, I think this is not correct. There is something. So, the current is starting from here, because this peak has to go to V into this current into the voltage across that VDS. Okay. So, I think this is not correct. VSW is rising from here. So, how can VDS should start changing right away? It should start changing from here only. Okay. So, it will remain VDD plus VF until here, because what is your VDS? VDS is nothing but VDD minus VSW. So, VSW remains VF until this point. So, VDD plus VF will extend until this point. Okay. But your current starts rising right from when you have a difference of threshold voltage across gate and source. So, this will peak here and this will start falling. And ultimately go to IDD into RP. And this is the point where current your okay. So, your current is rising from here, it will hit the peak, not really. Let me clean it little. So, your gate voltage, this is the point where you cross the threshold voltage. So, your current will start rising from here, and before you your source voltage start switch voltage, the VSW, the switch voltage starts dropping to 0. That means, you have attained the current of I load. So, it should peak before this. So, okay. Now, you have to take the product of the two. So, the point at which you attain the load current, that is where your VDS starts dropping. So, the peak power in the MOSFET will be at that point. So, it will look like a triangle, correct, and then your the VDS of your MOSFET is start dropping. So, the power will start again. So, the current is now full, but the voltage is start dropping. Earlier the current was 0, but voltage was full, so power was 0. Current is rising, but voltage is maintained. So, at a point you will hit the maximum point and then it will fall. Okay. So, what will be? So, this was 0, but this won't be 0. This will be how much? What will be this power?
IDD square
IDD P square R on P. Okay. Now, the same thing will happen when you are turning off. So, let us see when your So, what will happen to the current? When you are turning off. So, when you are turning off, your VSW will start decreasing, correct? But what will happen to the current? That diode has to become forward bias before the current will start flowing from bottom FET, the body diode of bottom FET before. So, until diode gets forward bias, the current will keep flowing through PMOS. But what is happening to the VDS? VDS is increasing. So, the current remains same, but VDS keeps on increasing. VDS keeps on increasing means the RDS on of that is increasing. So, it will see very high resistance, okay, but the current remains same. So, basically the losses will be very high, and that loss will be nothing but again the voltage across that FET multiplied by that current. So, this will start falling, but current does not. So, where was the current? Yeah. And this will happen actually when this MOSFET completely turns off, correct. So, in order to have the current flowing through that FET, that body diode, it has to be very weak or almost near turn offs. So, if your current starts dropping from here, this is the point where it goes to 0. So, where is your VDD? This current will remain. So, this is the point where your, so where will be the peak now? Peak should be again same point, okay. Now, the current starts dropping. So, okay. So, if I call it T rise or T on, let us say this is the turning on, T on P, and this is T of P. Let us make it small. Okay. So, they may be different, T on and T off might be different, because your rise and fall of the gate might be different, correct, and you do not know at what point exactly your diode will turn on, but usually the VDS voltage is almost full when it turns on. So, the current starts, and there are some delays associated with the power FET, the intrinsic delays of power FET, which might be due to the parasitic cap at the gate, sorry, not the gate, at the drain, which is the intrinsic cap of your MOSFET, okay. And there are some parasitic caps on the VSW itself when you design. These are some routings, and basically and usually this VSW is connected to the inductor externally. So, those pads will also have some capacitor. So, there will be some delays associated with that, but in the best case this is what you can achieve actually. In other cases it might be even worse. So, what will be the total power? So, I am just calling PSW, which means switching power, is the average power during T on P and T of P, and this is simple, half base into height. So, what is the voltage? the base is nothing but T on P. What will be this peak? Square, not square. VDD plus VF. Plus do the same thing during T of P so if VDD is much larger than VF, let us say, then you can approximate, and that is what you see in the textbooks. They do not consider that VF factor. But if your VDD is small, then you have to take into that account. Into, and you have to divide by TSW also, okay, switching period. So, this whole thing will be not VF. You can also write this I load, okay, because IDD is nothing but I load if you ignore the ripple. So, this is what you remember actually, but if you are given the values of VDD and all those, and you find that VF is not as small compared to your VDD, then you have to take into account that. So, let us say VDD is 10 volt, then VF may be a small fraction of that, then you can ignore it, will not affect your efficiency that much, but if VDD is let us say 1.8 volt or so, then you have to take into that account. So, this T on P and T of P you can calculate from your simulation, or if you are using external FET, then most of the time data sheet will specify that. So, you have to look at how fast gate is charging. So, that will obviously depend on your gate driver and the capacitance on this gate, and there are some intrinsic delays on the of the transistor which are specified in the data sheet. But if you are using on chip MOSFETs, you have to look at the simulation. But you have to remember, this is a significant factor for the external FET, but when you are using on chip, then this may not be significant as compared to the previous losses like dead time losses and gate driver losses. The reason is these on chip MOSFETs are very fast, so they can turn on much faster compared to the external FETs, which have other parasitics and intrinsic delays associated with them. Okay, so, for discrete power supply design, what power electronics guys do, they usually consider this as a dominant factor. So, the switching losses starts dominating for them. So, if you for all the switching losses, which is your dead time, your gate driver and this particular one, they will start dominating when FSW is very high. Okay. Some of them are a function of load and some of them are not, like your gate driver switching losses, but they all are function of your switching frequency. So, that is why most of the DC-DC converters or switching regulators you find in the market, maximum available today might be 10 megahertz or so, and the current would be like less than 1 amp or up to 1 amp, not more than that 10 megahertz. But if you are looking at a 10 amp kind of a current, you will see achieving even 1 megahertz is not easy with that, because these losses are very dominant and they will kill your efficiency.